Some analytical issues. Our aim is to define a representation of the Lie algebra. Unlike the compact group case or the finite dimensional case, you cannot define these Lie algebra operators from the whole space. We have to find a dense subspace. So the first subspace we'll be looking at what will be C-infinity vectors, smooth vectors. So these are going to be densely defined operators. So remember that our typical space is going to be an infinite dimensional space. In the case of finite dimensional representations, all the vectors turn out to be smooth. Okay, so that's why they are defined on the whole space. And we'll see that, so it turns out that one has to find a smaller space than the smooth vectors, called analytic vectors, and we'll find G action, the Lie algebra G action on the space of analytic vectors, and we'll see that we'll go further down to what are known as K finite vectors, and there would be a correspondence between the Lie algebra action and the G action. And so that's what you see in the case of finite dimensional or representations, right? There is a correspondence between the Lie algebra action and the Lie cube action, so let's say for simply connected groups, and we'll establish a similar thing. So that gives us some infinitesimal data of a reducible representation, and that will classify representations. Alright, so we start with C-infinity vectors. So I have a one-half space representation of G. A vector V in the space B is said to be C-infinity. C-infinity. Sometimes we say smooth. If the map x going to phi of x, so phi of x is an operator on V, so you simply apply it on this vector V. So I have a map from the group G to the representation space V is a C-infinity map. You see. Okay, so this is a condition which on the vector V. Okay, so such vectors are called C-infinity vectors, and it's obvious that it is a subspace, right? If V and W are smooth, then V plus W is also smooth. V is a Banach space. So it's a map from G to a Banach space. Usual definition of the derivative. There is a linear map. F prime will be a linear map from V2, boundary linear map. Well, we will go down to analytic vectors where the strongly analytic and weakly analytic are same. So, but here we take the strong derivative. So if I have a map, let's say F from let's say Rn, or in some neighborhood in Rn to V, well, you define in the usual sense. So the derivative is limit x going to 0, f of let's say x naught plus h minus f of x naught divided by h, but then you do the usual thing, right? Oh, sorry. It should have been right here. Okay. So just like you do this in several variables, you have a linear map x naught plus h minus f of x naught minus f prime x naught acting on h divided by. So this will be a bounded linear map, right, from wherever to V. So the usual definition of derivative, except that the space Rn is replaced by Rn. So it has to, everything will converge in the norm, right? You have a norm on V and convergence is once we go to analytic vectors, this instead of the strong definition, you can compose with the linear functional and go to complex numbers and the usual analyticity. The smooth vectors form a subspace, so that is CC, so we denote it by V infinity. Smooth vectors in V. Yeah, so this is a subspace. It's not. Well, we'll prove that it's a dense subspace. So that means there are enough smooth vectors for a representation. So that's the first proposition. But let's construct C infinity vectors to start with, and we'll see that that is a dense subspace. So this is called the guarding space. Guarding subspace. How does one construct this? So remember the pi f we defined yesterday. So I take a function in CC infinity. So smooth function with compact support. And then we define pi of f, right? So that's the Fourier transform. Pi is my representation. So we call pi of f. Pi of f acting on B. This is integral over G f of x ix dx for V. And these vectors, so pi f b, where v is an arbitrary vector and v, this collection of vectors, these are all going to be C infinity vectors. Okay, these are all going to be smooth. Well, why is that? I want to show something like this is C infinity. Apply the definition. So I have to apply pi of x to this vector and see if it is smooth. Right? So question is x going to pi x, pi f be smooth? Right? So if I put a, okay, so there are too many x's, so let's put a y here. So y going to pi y, pi f be smooth. Well, I apply pi y to this, so the y goes here, I'll have pi yx, but dx is invariant, right? So you can change this x to y inverse x. So I'll have an x here and y inverse will come here. So that is f of y inverse x. But f is smooth compactly supported, so you can differentiate that with respect to y. Right? So it's a smooth vector. So if I apply smooth compactly supported function to V, I'm going to get a smooth vectors. And if I take f to be a compactly supported smooth approximate identity, it is going to converge to V, so that is dense. Right? So let me write down that as well. If Fn is a smooth approximate identity, then, well, this is true for any approximate identity. Pi of Fn V converges to V. And so this tells me that choosing a smooth compactly supported approximate identity tells me that C infinity vectors are smooth. Dense. So C infinity is dense in V. Okay, so there is an ample supply of smooth vectors to start with. Now, we want to define an action of the Lie algebra on this smooth vectors. Okay. So you take some element in the Lie algebra. Okay. Define. So if I have a function f, let's see if I will define it. So for x in G, the Lie algebra, and V in V infinity defined. So the V infinity means smooth vector. So I can differentiate that. Okay, so define. Well, I'm going to define the derived representation or the representation of the Lie algebra. So I'll use phi dot for that. So phi dot of x. So whenever I write, sometimes I may forget the dot, but it should be clear from the context. Phi dot of x, where x comes from the Lie algebra, p equal to d by dt at t equal to 0 of phi of x dx. Right, so x dx is in the group, phi of this is the operator of v acting. Right? So this is a smooth function in t, right? That is why, because v is in v infinity, and so I can differentiate. So this is the definition of the action of the Lie algebra on v infinity vectors. Okay, of course, you have to verify that the Lie algebra elements will take smooth vectors to smooth vectors. Of course, if you have a smooth vector and you differentiate it, you are going to get a smooth vector. So that's easy to verify. X in G, then phi of x v is in v infinity for v infinity. So smooth vectors are mapped to smooth vectors. Well, this is easy because group multiplication is v infinity, right? So applying another pi x is not going to change anything. And similarly, if you differentiate a smooth vector, you are going to get a smooth vector. And phi dot of x v is also a smooth vector for every Lie algebra. Okay, so you have an action of the Lie algebra on the space of smooth vectors. Now, as I said, our aim is to set up a correspondence between the action of the Lie algebra and the action of the group, but it's not. It turns out that it's not enough to look at or same infinity vectors is somewhat big for this correspondence to be set up. We will have to go down further to analytic. So I'll define that, but before that, let us. So let me say that this is actually an action of the Lie algebra. So this is something I have seen for working groups already. Yeah.
Is it easy to see why smooth vectors are not enough?
Well, there are different representations with same set of same infinity vectors. Let's see. I don't have.
There was a comments made that some Taylor series does not converge.
Taylor series does not. Well, for smooth vectors, the Taylor series may not converge always. The point is, you can have different representations with the same set of C infinity action. So apparently, this C infinity action does not distinguish between certain representations. That's why one has to go down further to analytic and K-finite. The one-one correspondence is true only when you go down to analytic. But yeah, I don't have an example. I don't think it is that easy to get down. Okay, so let me complete this proposition. So this is something you have already seen. If you have a representation of the compact group, you can differentiate. You get a representation of the Lie algebra. So here it is a representation of the Lie algebra. Okay, so which means that phi dot of x comma y is whatever it should be minus phi dot y. So you get an action of the Lie algebra. Now, as we have seen in the case of compact groups, Once you have an action of the Lie algebra, it extends to an action of the universal and everything. Okay, so I should tell you what it is. So quickly go through that. So universal and algebra. We may not need all of this. We need only a particular element called the Casimir from the universal and everything. Algebra, it is good to know that the representation extends. So I'll quickly go through what it is. So first start with GC. GC is the complexification of G. In our case, it's simply SL2C. Right? So this is complexification of G, and in our case, it's just SL2C. The universal enveloping algebra is denoted by U of GC. So this has a certain algebraic definition first, but we will not bother about that definition. We will think of them as left invariant differential operators on the groups. Okay, so the algebraic definition is you look at the tensor algebra and then quotient it with a certain two-sided ideal. So that is where TG, that is the tensor algebra. So this is I should say C, there is some GC tensor GC and so on. Then I should
C tensor
sorry?
not just GC. C, there is some GC, there is some G.
C. Okay, yeah, sorry. Yeah, there should be GC to start with. Yeah, thank you. C. And so on. Okay, so the Lie algebra sits inside the universal. And one has the Poincare-Birkhoff theorem, which gives a basis for the universal enveloping algebra. You take a basis for G and then look at the monomials defined by those bases. That will be your basis for GC. So basis for GC given by the Poincare-Birkhoff theorem. So what you do is, so in our case it's three-dimensional, so I'll write only that. So take x1, x2, x3 basis for GC over C. Then you look at powers of in the same order. Okay, so powers of so x1 to the, let's say, j1, x2 to the j2, x3 to the j3. Okay, so j1, j2, j3, they're all. Okay, so this is a basis for okay. That's a Poincare-Birkhoff theorem, and as I said, we'll think of them as left invariant differential operators on G. Okay, so each Lie algebra element gives a derivative, first order derivative on G, which is a left invariant differential operator. So this is like the directional derivative on right. So for, let's take a smooth function and take a Lie algebra element. We want to define a derivative, right? So we have already seen this. So define x tilde of f at the point G to be d by dt of equal to 0, f of I want it to be left invariant, so you put the x dx on the right side. Right, so this is the directional derivative of f in the direction of x at the point G. Right, so x tilde is a first order differential operator which is left invariant. Left invariant means invariant with respect to the left translations. Right, if I change G to let's say hg, that's not going to change. Right, so it's like the usual partial derivatives of right. So the left invariant first order differential on G. So the x1, x2, x3, the basis will give me those three first order differential operators, and the powers will give me the higher order differential operators. Okay, so all of UGC can be thought of as left in. So of course there is something to be proved that map is a 1-1-1-2 map. But once you prove that, the universal enveloping algebra, even though there is a algebraic definition, you can think of that as all the algebra of left invariant differential operators on G. And once, because of that basis and so on, it's easy to see how it extends, right? So if I want to define, so I have pi dot of the Lie algebra, I want to extend it to the universal enveloping algebra. This tells me what to do. Of course, you still have to prove that everything is well defined and so on. So pi dot of something like this would be pi dot of x1, you apply it j1 times, and pi dot of x2, j2 times, and so on. Right. So I'll write that as a proposition which says that any Lie algebra action will extend to an action of the universal enveloping algebra. So again, this is something you will see, or you have already seen in the case of combat link. So if this is the formal statement, if A is a complex associative algebra, with identity, and you have a Lie algebra action, so G A linear map such that it respects the Lie algebra action. So phi of x bracket y is px py minus py x. So the right hand side multiplication is in A. So it's a Lie algebra representation on A. Right? Then it extends uniquely to UGCs. And phi extends to a unique associative algebra homomorphism to UGC. Okay, so the product in the UGC as say product of differential operators or whatever will be preserved by this extension. In other words, because of this action of the Lie algebra on smooth vectors, we can extend it to UGC. So V infinity become a UGC model. So chronology is okay. So this is a purely algebraic statement. There is no. This is a dense subspace, right? It's not a closed subspace and so on. There is an action of UGC on V infinity, which is extending from the Lie algebra. Okay, so now we are in good shape to define analytic vectors. So analytic vectors are defined exactly like the smooth vectors, except that the condition is that the corresponding function is an analytic function. And we'll prove that they are dense in V. So again, there is a ample supply of analytic vectors. Then we need to prove that the k finite vectors are also analytic. So it's going to take these two lectures to prove all this. Vectors. So we will hopefully finish with the major theorem today. Vectors. Extendation G. V infinity is called analytic. If the map x going to pi xv is analytic, and As usual, the analytic vectors form a subspace, that is clear. If V and W are analytic, then the sum is analytic, and the analytic vectors will be called V omega. Okay, so V omega, so this is analytic vectors. V, and of course V omega is contained in V infinity. Of course, right now we don't know if there are analytic vectors. Okay, it's only a definition. Okay, so analyticity, so just a remark here, so that whether weak or strong, it's all the same. F from, let's say, G to V is analytic, which means you have a power series expansion, right? You take a point, there is a neighborhood where power series expansion, which will converge in V, which is same as saying weakly. Weakly analytic, which means that is alpha of F. So alpha is a continuous linear function along V, which takes values in the complex plane. So now alpha of F would be a map from G to the complex plane. So that is the usual function is analytic. Okay, so for analyticity, weakly and strongly are all the same. So we may use that when we want to prove something is analytic by composing it with a linear functional and then bringing in an elliptic equation. So another remark. That's 1, 2. V omega is also UG module. And in that there is a UGC action there. If I differentiate an analytic vector, I am going to get an analytic vector, except that we still don't know if there are analytic vectors. Okay. And the Taylor series, so that if V is an analytic vector, then we can expand. So pi of x, so you take a x in the Lie algebra and add, so this is going to be the usual Taylor series, pi dot of x to the n by n factorial acting on V. So this is simply expand t going to pi of x dx V at t equal to 0. Right, pi dot of x is defined to be the first derivative at t equal to 0, and the higher derivative will give you the higher powers of pi dot of x. So, and that will converge, right, because V is analytic, and this is simply the Taylor expansion at t equal to 0. Okay. So let me write down an easy theorem, and then define a certain class of representations, and then we will prove a somewhat major theorem. Okay. So let V. So we still haven't produced analytic vectors. We'll do that, and we'll show that this action of the Lie algebra will correspond to appropriate actions of the Lie group, right? So by V summation of G. So all this, whatever I'm saying, is actually true in general for semi-simple Lie groups with finite center. You don't have to stick yourself for all these definitions, but soon we are going to restrict ourselves to a simple. So let W be a subspace. So whenever I talk about C infinity vectors, analytic vectors, and so on, these are all algebraic subspaces. There is no closeness assumption. But whenever I talk about the G action, invariance, reducibility, everything requires closeness of the subspace. Okay. So this is the subspace. Invariant under, let's say, pi dot x, where x belongs to G. So it's invariant under the Lie algebra action, right? So algebraically, so you take something in W, apply a Lie algebra element, you go to the same space. Then the closure of W is invariant under the group. Okay, so then W closure is invariant under phi of x, where x, small x belongs to capital T. Right, closure, because remember invariant subspaces are defined to be closed subspaces which are invariant under the G action. Right, so whenever I go to the group level, I look at closure. So with respect to the Lie algebra action, if I have an invariant subspace, I take the closure, I get an invariant subspace for the for G. So, right? So in particular, if I want this to be irreducible, then the Lie algebra action will have to be irreducible at the analytic vectors level. Well, this is an easy proof from the Taylor series. Right? So one line proof. If V is in W and X in G is small meaning the neighborhood of 0, then I look at phi of x specs acting on V. This, because of the Taylor series, I have phi dot of x to the n by n factorial V, and this will of course belong to W closure, right? Because phi dot of x leaves W invariant. So any power of phi dot of x will also leave W invariant. So all the phi dot of x to the n, V is in W closure. In W. So when I sum up, I'm going to be in W closure, right? And if so, and we also have the map from G, right? A neighborhood to a neighborhood of identity, the X map, which is a diffeomorphism. So this neighborhood is taken to a neighborhood in G, and G is collected, and this neighborhood will generate G. Right? So if all the elements from this neighborhood of identity in capital G leaves W closure invariant, then all of G will leave it invariant. Okay?
So the connected, you mean the capital G is connected?
Yeah. Well, I should have said that, but we are looking at a self-model. Right. So if I have a connected topological group, any name generate G. Okay. Just take the powers of this and take the union. That's an open subgroup. It's also connected. It's also closed, so it will be all of G. So to show that W closure is invariant under all of G, it is enough to show that it is invariant under a small neighborhood of the identity, and the small neighborhood comes from the X map with a small neighborhood of 0 in G, and the Taylor expansion tells me this. Yeah.
In the previous preparation, you need x to be small, by x.
Here.
Yeah. Previous Taylor series.
I don't think so. Well, so the neighborhood may depend on X, right?
What you have written, that pi for any x belongs to b, pi exponential of x b as a Taylor series. And here also given.
Yeah. So here, you can assume it to be small so that everything converges if you want.
X has to be
So, I mean, you want to say whether I should take X to be small or not, right?
If that is true for every x, then we don't have to.
Assume that X is small, yeah. That's
Yeah.
need X to be small, yeah, exactly.
I have a question.
Yeah.
So if it takes the smooth vector, then is the omega W closure going to be bigger than like, so?
Can you please repeat?
So if you take smooth vector instead of analytic, W is
Smooth vector, so V infinity, yeah.
Yeah, and W is invariant. So this W bar is going. So I'm saying like how do you construct it that everything is going to be W bar? Is it going to be more than W bar?
I don't really understand the question. So, if instead of analytic, if I had C infinity, I don't know if W bar is invariant under G from this argument, and I need the Taylor series. But if it is contained in V omega, and then this tells me that W bar is invariant under G. W bar is not going to be bigger, right? W bar is fixed. If W is given, W bar is fixed. The closure is fixed. That is happening in the original Banach case B.
It can be.
Oh, when you keep applying G, you may get bigger. Yeah, that can happen. So this is going one way, right? So starting with the invariant subspace and the Lie algebra action of analytic vectors, I can go upstairs, right, to the invariant subspace of G. So here is another definition, admissible. So these are the representations which are classified using the infinitesimal method. So phi B, the representation of G, we call, so we had those Vn's, right? Those are vectors which transform according to the nth character of the maximal compact, which is SO2. V phi of A theta V equal to A to I n theta V. So Vn's were closed subspace and algebraic direct sum of the k finite vectors, which was dense in V. The representation is said to be admissible. Phi is said to be admissible if dimension of Vn is finite for every n. Of course, none of the Vn's may be 0. So we will stick to the class of admissible representations because some of the things may go wrong if we go out of that class. And now we are in a position to state a major result, which says that unitary reducible representations are admissible, and we can say the dimension of what the dimension of the ends are. So we'll prove that and stop. I hope I should be able to do that in next few minutes. So now we are looking at unitary reducible. So V is a Hilbert space and phi is unitary. Okay, so we have unitary irreducible representation of SL2R. Then, and Vn is what we have defined. Into the I n theta V for every theta, so let's not write that. Then dimension of Vn is less than 2. Of course, it can be 0. Some of the Vn's may not appear, but if it appears, its dimension is 1. So, in particular, the unitary reducible representations are admissible representation, and whatever infinitesimal classification we are doing will be applicable to unitary reducible representations. Okay, so that's precisely our aim. In 15 minutes, we will try to do this with appropriate. So I'll just give you the certain steps which are easy to verify. Okay, so I'm not going to write down every detail. Now, a few remarks. So the dimension is bounded by 1. The 1 comes from because of SL2R, because the corresponding representation of K, the maximal compact, they are all one dimension. In general, if you have a simple Lie group with a finite center and so on, and if you take a unitary reducible representation, V instead of Vn, you will define V delta, and delta is a representation of K. Right? So you look at all those vectors which transform according to the representation K. Here the dimension V delta will be equal to delta d delta square, where d delta is the dimension of the representation. Okay, so that is the major, in fact, I think it was written down yesterday. So that's a major theorem to Hirschfelder, which in the case of SL2R is not very difficult to prove. Okay, so let's start with the proof. Let's say step 1. So we defined certain class of functions. So define CCG was already defined, right? This is the continuous function with compact support. Now we look at certain functions, so class of functions which transform according to representations of K. So I'll put an N and M here. Okay, so the N is on the left, M is on the right. So this is going to be the class of functions F in CCG. So first of all, it's compactly supported continuous, but with respect to K, it acts like so it has a certain transformation on the left with respect to the nth character and on the right with respect to the mth character. So f of k theta x k phi is going to be equal to e to the minus I n theta f of x times e to the minus I m phi. Okay. So whenever there is a k on the left, that comes out as the nth character, right? Complex conjugate of the nth character, and similarly here. Both minus. Yeah. Yeah, well, for the definition it does not matter. So, well, I defined this, then this is easy, then the algebraic direct sum. Algebraic direct sum CCG and M is element dense in CCG. Well, it's actually dense with respect to the supremum now, but that's not worry too much. It's enough to have the element denses for our. So that is simply you expand a function here in the k decomposition in the k variables. You will get finite sums like this, right? That will approximate that. Okay, so that's a straightforward computation. Step 2. So that is a class of functions. We'll see where that comes from. So the Vn's will be obtained by applying such functions. CCG. So this is pure computation, and I'm convolved with CCG LQ. So I'm looking at two such spaces with, let's say, characters. So here I have n on the left, m on the right, and l on the left, q on the right. Then this is 0 if the middle ones don't match. If m is not equal to l, and it's contained in, if m is equal to l, it will be contained in nq. So CCG nq. If m equal to l. Okay. So that is one. So these are all completely trivial, right? Because this is a convolution. So if I write down the convolution, I have f of x y inverse g by dy integral over g, right? And I want to know if some convolution survives or not, right? So I just change y to change y to k theta y to k theta y, where k theta is coming from k. I'll have a k theta here, and this becomes y inverse k theta inverse, right? And dy is invariant under the translation. So I'll have f of x y inverse k theta inverse g of k theta y dy. But g comes from this space, so there is an L here. So this will give me an e to the minus I k theta L, and f comes from the first space, so there is an m on the right. So that gives me e to the, there is a k theta inverse and there is a minus with respect to the character. So I will have an e to the I m theta, right? So L theta and m theta, right? and the k theta disappear. So it's the same function multiplied by this factor. So this will be 0 if they don't cancel each other. So if n was not equal to L, it will be 0. Right? If n equal to L, of course, it doesn't give you any information, but then you put it here and then change the variable and you will get that. Okay, so all these are straightforward computations. So number 1, 2, ECG and star. Well, this is trivial. ECG M. Well, what is star? F star of x is. This is the star operation in L1. F of x inverse bar. So when you take the inverse and the complex conjugate, the M and N will change the order. The CCG N. Okay, so the same N. Then this is a commutative algebra. Commutative with respect to convolution. So this is slightly non-trivial. I'll not do this. And this is true only for SL2. Okay, what I mean is, if I have a general semi-simply group with a finite center and so on, if I look at the corresponding object, so I'll have a delta, that's not going to be commutative. No, then the V delta will be one dimensional, right? So here the one dimension comes because this guy is commutative, and if I apply the representation of this to the space, I am going to get V. Okay, so we are in shape now. Okay, so proving this requires some work. I don't know if you can write down the definition and see that it is true. It might be very messy, but there is a Gelfand trick. So some of you at least know about Gelfand pairs and so on. There is a Gelfand trick. If there is a anti-automorphism of order 2, something happens. Okay, and that happens here. Right? So, is there a problem?
Probably that is because it should be NM goes to PN, right? Like the other calculation showed that CCG NM acting on V goes to PN.
Number 2 is it PN or DN? DN.
Okay, so let us check this. Okay. Or maybe we'll do that in the tutorial. Let's come.